Python is versatile. When I started programming in Python, I used it as a scripting language. My object-oriented programming was typically done in Java or C++. Well, today, I use Python for both. A quote from Gemini: Python is a versatile programming language that strongly supports object-oriented programming, or OOP. This paradigm models real-world entities as objects with attributes and methods, promoting code reusability, modularity, and maintainability. Key OOP concepts in Python include classes, objects, inheritance, polymorphism, and encapsulation. Python is flexible. We can use it as a scripting language or an object-oriented programming language, as this image shows, using some real code examples, and we'll look at some more coding examples. Let's start with scripting. Python excels at automating repetitive tasks. If you're doing something tedious, consider writing a script. It'll save you time and reduce errors in the long run. Scripts range from simple command sequences to complex programs with functions and external modules, offering flexibility for various automation needs. In this example code, we are using Python for scripting. Our task is to organize files into subdirectories based on their file extension. As you know, the extension of a file tells the operating system and other applications how to treat the file. And Python files, of course, have the extension .py, text files .text. If you use a Microsoft word processing document, you have a .docx extension on files, and so on. Hopefully you have by now figured out how to set your file finder or viewer to show you those actual extensions. They are hidden by default. This script gets all files in the current directory, and for each file, it determines the file extension. It then creates a subdirectory for each unique extension if it doesn't already exist, and then it moves each file into its corresponding subdirectory based on its extension. So this can help you organize cluttered directories by grouping files of the same type together, making it easier to manage and locate files. I posted a warning here after I tested this code myself, because I really wasn't thinking, and I accidentally organized an entire directory that I had not intended to organize. So the warning here is, do not run this code in a directory unless you actually want to organize the folder that you're running it from, as this code will in fact organize that code. So if you do have a directory you would like to organize, you can copy this code, paste it, save the Python script into any directory that you want to organize, and then at your terminal, go to that directory and execute the script. It will organize the files. We import a couple of Python standard libraries to make this happen. The OS library, which stands for operating system, and the shutil library, so that's shell utilities. The first command is to get the current directory, and that's an OS command. So your current directory is going to be part of your operating system, and the os get cwd command will return the current directory that you're running this script from. So we set that equal to a variable. To list all the files in the current directory, we again use the OS library with the command listdir for list directory. And that gives us a list of all the full file paths of all the files in that directory. So we set that to a variable, and then we use a for loop to iterate through all of those files. Now, keeping in mind, files is now a list of fully qualified paths for each file in the directory. The first thing we do is skip directories, and we can do that. So if there's subdirectories in the directory that we're processing, we would just want to skip those. And there is, within OS, the path submodule has a command called isdir, So for file in files, so file is the string path. So we check to see if it's a directory. If it is, we continue. And continue just pops us out of this for loop. We get the file extension by using another command from os.path called split.ext. Splits the extension, and in this case, we don't care what the file is called. We only care about the extension. So I'm just going to use an underscore to save the first part of that path, and then extension to save the extension that I want. And then I want to remove the dot. So I'm going to, for example, if it's a .py file, I just want pi stored in extension. So I remove the dot from the extension just by recognizing that a string is a list of characters, and using this notation 1: says to take the characters from position 1 on, which will exclude that character at position 0, which is going to be a dot, which was returned by the split extension command above. If after doing that, I indeed have an extension, meaning the file did have an extension on it, I'm going to create a directory for this extension if it doesn't exist. So I use another command called exists from os.path, and I say if os.path does not exist, then call makeDirs, another os function, to make directories, and make directories for that extension. So what I'm doing here is, for example, for all Python files .py, I'm going to make a directory that's simply called pi and store all those files in that directory, and so on for the rest of the extensions. Next, I'm going to use another command, this one coming from shell utilities, shutil.move. So this is the move command. If you're familiar with Linux or Unix at the command line, shutil is going to be similar to those types of commands. So I can move my file to the new directory, and here I will join the extension that I got above, which is the directory that I just created now, with the file path. And move the file to there. So I'm moving the file to this new directory that I just created. And then I'm just printing that I moved file to extension folder. Of course, if there isn't an extension, then I'm going to skip the file because it has no extension. And then at the end, I'm going to print file organization complete. So this type of activity is very useful. What I like to do, if I find myself doing anything where I am repetitively using the mouse, clicking, dragging, dropping, or even repetitively typing commands at the command line, that tells me it's time to create a script. If I'm doing something repetitively and I'm going to want to repeat it again, I'm going to create a script to do it for me. The script is going to make it easier to repeat, and it's going to make it less error prone. You'll notice in this script above that there is no main function. It's just simply a list of ordered commands along with the imports that I needed to get the modules from the Python libraries. So what is main? Why do we sometimes see it? So you've probably seen Python scripts with a main function. Main is an optional convention that we use to structure code and control its execution when the script is ran directly versus imported as a module. So a lot of times when we write a script, we may want to reuse the functions in that script in other scripts or other programs. And when we do that, we're going to import our script. However, we might also want to run the script directly at the command line. And that's what main allows us to do. So the statement if name equals main is simply asking, is this being ran or executed from the command line versus imported? So in this script, this main function will execute. So if name equals main will execute, and it calls this, you could literally have any code you want in here. You could have your entire program in here if you'd like. But the convention is to have it call a main method. And the main method is only executed when the script is ran directly, and it is not executed if you import it as a module into another script. So I have this greet function here, and maybe I want to reuse the greet function in other programs that I'm creating. So I might be importing this file in different programs, but I also might want to test this file. I tend to use this construct here for testing a file to make sure that all of the functions within that file run correctly before I start importing it into other modules. Or if I have a program where I want the program to be command line executable versus imported, and I want it to be able to do both, then I might have a main function there as well. So main is optional. Because Python can be and is a scripting language, you can simply just list the commands that you want to execute as we did here. You don't actually need functions, but then we use them to organize code. And certainly you don't need a main function or if name equals main, but again, it allows you to have that flexibility of either executing the code at the command line or being able to import it to use its functions in other programs. As a tip here, in some text editors, I use Sublime, and this is true in other text editors as well. If you type IFM followed by a tab, it will automatically insert this entire code snippet. If name equals main, call main. In fact, I have used this so extensively that off the top of my head, I have a hard time remembering the exact syntax for this because I just haven't had to type it in so long. So try your text editor and try typing IFM tab and see if it does that for you within a Python file. Of course, the file will have first needed to be saved with the .py extension so that your text editor recognizes this as a Python file. And if this doesn't work for you, I'm sure if you look, you will find that there is some other shortcut code snippet that allows you to get this very common snippet of code with a couple of simple keystrokes. So that is using Python as a scripting language. I used Python exclusively as a scripting language for many years before I even began to look at it as an object-oriented programming language. But now, like I said, I exclusively use Python when I have a choice, and I use it for OOP purposes as well. So what is object-oriented programming? You've probably had some experience in this if you're coming here and looking at the tutorials on this site, but if not, just a quick review at a high level. Objects in OOP encapsulate, meaning they encompass or keep together in a package, data and behavior. Data is the state of an object, so it describes the state of something, and behavior are methods that can be executed. So for example, if you think about a car object state might be its data about that car. So make, model, year, color, things like that. And then behavior would be things like parked, driving, stopped, and so on. And those are implemented in object-oriented programming as methods. So encapsulation, it's simply a word that we use. It's nothing meant to be confusing. It's simply saying that we're taking the state and the behavior of a thing, which we call an object, and we're putting it all together in a package. Thus, it's encapsulated. This allows for modular, reusable code. And that is the whole point of object-oriented programming, is to keep our code modular and reusable. Modular meaning you can break it down into smaller modules that can then be reused, so you're not writing the same code over and over. And it also allows us to maintain state across different instances. This is a key reason to create a class. So what is an instance? We'll look at some examples, but if I create a class, for example, in this image, I've created a class called character. The character has some data, so it encapsulates some state. And the only state I'm going to keep here is the name and health of the character. So this is a fictitious game. This character is going to have a single behavior, and that behavior is attack. So I'll implement that as a method. So this image of a class, character class, is loosely a UML diagram format, missing a little bit of the details, but generally unified modeling language format diagram. And if I want to create multiple characters, when I create characters that inherit from this character class, we call those instances of the class. They're also referred to as objects. So if you hear instance or object, we're just talking about a specialization of a specific class. So a character instance might be a hero, a character instance might be a villain. So this is the main reason that you want to create classes, so that you can contain the state of the different instances. So a hero can have its own health, a villain can have its own health, and they're both derived from the same characters, so they both have an attack method, but they can each maintain their own state. So if I change the health of the hero instance, it does not change the health of the villain instance, and vice versa. So we're able to maintain the state that way. And of course, their name is also part of their state, and they have different names, but they're still both characters. That is the main reason to create classes, but classes are also useful for simply organizing your related functionality, implementing inheritance and polymorphism, which I won't go into until the end of this video because some of you might not be interested in the details there, but I will go into more detail on both of these topics towards the end of the video. Or if you're creating interfaces for a complex system, creating classes helps to organize access to that interface. So you should only create classes when the benefits outweigh the added complexity. So for example, in our script up above, there was no reason to create a class here. We could have implemented this script by using object-oriented programming, but it would have been overkill. There was no need for it. There was no compelling reason to have it. And so don't automatically go to classes if you don't need them. If a script will suffice to get the job done, then write a script. So it takes a little bit of practice, and indeed it's a bit of an art to determine when you should write a class versus a script. A simple script. But be aware that when you create classes, you're adding some overhead. So if the benefits do not outweigh that added overhead, that added complexity to your code, if it's just a simple task that you want to run, functions or data structures will often suffice for that. So don't create classes unless you need to create a class. In the example code below, I'm going to implement this diagram shown above. So the character class with the two instances or objects. And this example showcases Python's OOP capabilities by creating this simple game. So it defines a character class with attributes, name and health being the attributes, and a method, attack, to define the behavior. So the attributes define the state and the methods define the behavior. Then I create two objects or instances, and I've named them. And then I show how they interact by attacking each other. So this is going to be a very simple program. Very simple indeed. It's just this little bit of code that you can copy. And this is safe to run. So this creates a class called character. Every class needs a method that initializes the class. The syntax for that is double underscore init double underscore. And then the first parameter is always self. Self can be the only parameter, in fact, or you can have additional parameters here. When I instantiate a new object or a new character, I want to give that character a name and a starting health. And so I'm going to include that in the init function. So init short for initialization. And when we're using classes, we always want to use the keyword self to refer to the class that we're currently working in. So when a new character is initialized, I'm going to set its name, so self.name, equal to the name argument that is sent, and the health equal to the health argument. So self.health equals health. And here I'm going to print out that the character was initialized with health. So I'm going to print out the name and the health that was initialized. And this function is typically really the only function that you need to create a class. If you have methods or actions that you want the class to be able, the objects of the class to be able to perform, and any methods that you would like to share between all objects of the class, you would implement them here as part of the class. So the attack method, again, because it's part of a class, the first parameter is self, and then the second parameter is target. And here, target is actually going to be another character. So it's going to be another instance or object of this class. So the first thing I'm going to do, if a target is attacked, is I'm going to decrement the target's health by 10. So health minus equals 10. And then I'm going to print that this character, self, name, attacked the target character name. And then I'm going to print the target's name now has target health. And we'll see what this output looks like in a minute. So this is extremely simple. We initialize player 1 and player 2. So player 1 is a character, and this is how we initialize an instance of a class. So we're creating an object. Player 1 becomes an object. We use the name of the class, and by convention, we like to use a title case for class names. That helps us identify that it's a class. That's a convention that is commonly followed. And when I initialize an instance of this class, I need arguments for each of the expected parameters. So name and health. So I'll give each of these characters a name and an initial health. So I'll initialize the hero with health 100 and the villain with health 80. And now I have these two objects. They are both characters, so they share the same types of attributes, but have different values, and they have the same method, so the same behavior. So I use player 1 to attack player 2. So the attack method has a parameter target, which is expecting another character. So the argument that I send is player 2. So player 1 attacks player 2, and then player 2 attacks player 1. If you copy and run this script, you will see this output. So from this first line here, hero initialized with 100 health, villain initialized with 80 health. After calling that, we get hero attacked villain. Villain now has 70 health. And the second call, villain attacked hero. Hero now has 90 health. So that's a very simple example of implementing a class, creating objects of that class, and using the methods on those objects. As promised, to take a slightly deeper dive into classes and what we mean by inheritance and polymorphism. These, again, are just terms that are commonly used to describe classes, but they mean things that are... thank you, Astro. I think my robot thought I was asking a question. Sorry about that. In any case, these terms, while widely used and often come up in interview questions, if you happen to be learning Python to get a job, writing Python code, you should certainly know the definitions of these terms and what they mean, but the meaning behind them is actually much more simple than the word implies. So inheritance is simply a mechanism in object-oriented programming where one class acquires the properties and behaviors of another class. There are a lot of different ways these classes get referred to, so not to confuse you further, you should understand that when you hear derived class or child class or subclass, these all mean the same thing. These are different words to talk about the same thing. And this is the class that is inheriting from the base class, parent class, or superclass. Again, these all mean the same thing. And these definitions will make more sense as we work through an example. So in this example, we just want to demonstrate Python's class inheritance and polymorphism. And incidentally, inheritance and polymorphism, the concepts in object-oriented programming, are the same across object-oriented programming languages. So the concepts themselves will remain the same, but we're going to look at how this is implemented in Python, which will have a slightly different syntax than some other object-oriented programming languages. So we first create a parent class called animal. Remember, this parent class may also be referred to as the superclass or the base class. The class animal initializes with simply a name of the animal, and it has two methods, make sound and move. And the defaults for make sound are going to be noise, and the default for move is going to be walk. And instead of actually performing some action here, we're just going to print something to the screen to demonstrate. Then we have a child class, dog. So the child class, also known as the derived class or the subclass, is going to inherit the methods and attributes from the parent class. So when I create this dog class, if I put as an argument to the dog class the class that I want to inherit from, animal, what I'm saying with this syntax is the class dog is an animal. This is what we sometimes call an is a relationship. A dog is an animal. Now I have options. I can leave it as is and simply keep the dog class such that it has the same actions. It's going to make the sound noise and it's going to move and walk. But I can also override those methods. I can say, I want the dog to do something a little different than other animals. So I'm going to override those methods. I'm going to override the make sound method. I'm going to keep the name the same. But instead of printing noise, I'm going to print woof. And I'm going to override the method move and keep it the same, the name the same, but instead of printing walk, I'm going to print run because I think a dog will run rather than walk. So I'm saying override, and override is a concept related to polymorphism. So now the make sound method and the move method are polymorphic, meaning they have more than one form. And it's going to behave differently depending on what type of object calls the method. Was it called by an animal object from the base class, or was it called by a dog object from the derived class? I'll create another class that inherits the parent class. We'll call this one a cat. So the cat class is going to also override make sound and print meow. But then we've decided the cat is probably just going to walk. So I'm not going to override the move class. And so you have a choice. When you're inheriting from a parent, you can either keep all of the methods as is, or you can override the methods to do something different for that subclass or that child class. So our dog overrode both of the methods, in the parent class. Our cat overrode one of the methods, make sound. And then I'll create a third animal, bird, which also derives from the animal class, so it inherits those methods. And I'm only going to override the move method for bird because a bird is not going to walk, it is going to fly. And from here, I have created one parent class and 3 child classes that inherit from the parent class. Now I can use these classes. I will create a list of animals, and each animal will be an object of one of my child classes. So dog, and the only requirement here, note that there was no init in these subclasses. So they are going to, by default, then use their parent's init method. And that method requires a name be sent. So I didn't have to repeat this for each of my subclasses. I can just use this from the parent class because my child class inherits everything that is in the parent class. So when I create a dog, I'll give it a name, and then I'll create a cat and give it a name, and then I'll create a bird and give it a name. Now I can iterate over my array of animals. I can get the name of the animal from animal.name. So I'm saying for animal in animals. So now every time I iterate this loop, animal is the next object in the list. So the first object will be a dog, the second one will be a cat, and the third one will be a bird. I can get the name by calling the name property on the animal, and that property is coming from inherited from the parent class. And I'll just print the name. And then I'm going to call the polymorphic methods. So now both of our methods are polymorphic, so they are going to execute something different. Even though I'm calling the same method name, it's going to execute something different depending on what type the animal is. So what type is the animal object? So the first animal being a dog, it's going to execute make sound for the dog and move for the dog. Same with the cat, is going to execute make sound from the cat, and then it's going to execute move. And since cat did not override move, it's going to execute move from the parent class. And then when I get to the bird animal and I call make sound, it's going to use make sound from the parent class because bird did not override make sound. But it's going to use move from the bird class because we did override move here. So let's go ahead and run this. Let's run this code. I'm going to copy this one, get my Sublime editor open here, paste it, save it, and I will save this as pets.py. So I have my code saved there, and I will go to my command line, and I see pets.py got saved here, and I can execute it. See what it outputs. And you see the output. So let's look at the code at the same time with the output here. So we have our animals, dog, cat, and bird. And for iterating through that loop, that list, animal and animals, we're going to print the name, and then we're going to call make sound, and we're going to call move, and both of those have a print statement. So the first one, our dog, prints Snoopy woof run. Our cat prints Garfield meow walk. And our bird prints Tweety noise and fly. So that's a very trivial example of class inheritance and class polymorphism in Python. If you want to learn more about inheritance and polymorphism, and again, I would stress that if you're planning to interview for jobs as a Python developer, you should certainly be able to answer questions around these terms, the definition of the terms, and be able to use them intelligently. And if you're if you're like me and you have a hard time committing raw facts to memory, it helps to repetitively find different ways that these are explained and different ways that they are described. So I gave another example of the details here. So inheritance, dog, cat, and bird inherit from the animal class. That is inheritance. This means they have all the attributes and methods of an animal, but they can override and they can also add their own methods. So I could have, and in addition to overriding the parents' methods, I could have added additional methods. For example, a bird might have some actions that a dog and cat don't have because a bird has wings. Polymorphism is demonstrated in this code. The methods defined in the base animal class are overridden in the child classes. This allows us to treat different animal objects as if they were of the same type, which they are, animal, and call the same methods on them, knowing that the correct implementation of that method will be executed. So that is polymorphism, specifically class polymorphism. For some more examples of inheritance and polymorphism in Python, I like W3 schools. Just going to click on the second link here, polymorphism. Now that first link goes to inheritance here, just right above. And you can read through these to get yet another example. Like I said, repetition and practice will help commit these things to memory. Polymorphism, I talked a lot about class polymorphism. That was the example that we gave, but polymorphism also exists simply at the function level. For example, the length function in Python is a polymorphic function. It behaves differently depending on what the argument is. So for example, length x here, if x equals hello world is a string, for strings, length returns the number of characters in the string. If length is a tuple, as in this example, then length returns the number of items in the tuple. If length is called with a dictionary, it returns the number of key value pairs in the dictionary. So functions can also be polymorphic. We talked about class polymorphism, but functions can be polymorphic outside of classes, and the length function is a good example in Python of a polymorphic function, which is going to behave differently depending on what argument you send to the function. So I hope that gave you a good starting place to dig deeper into inheritance and polymorphism. And I hope you enjoy practicing writing scripts in Python and also using Python for object-oriented programming.